And so I'd like to share with you actually some of the design principles that are related to these math sims, and some of these will be familiar to you, others might be new to you, but hopefully try and make some connections with at least one of the simulations here before you start getting into your lesson development, which I think what you're going to be doing later today. So really what are some of these design principles, and what are productive ways to kind of leverage these principles to support student learning? So oftentimes, I mean, think about when you are looking at instructional materials, textbook, other resources, oftentimes you're expected to infer, what was the designer's intent here? Like, how is this expected to be used? Not that you need to know everything about that, but it can help so that you don't miss some potential questions that could be asked or uses of this. You had a look at some sims yesterday. So just from your inference of what you've been noticing, what are some design principles that you would propose here? What are some conjectures you can make about design principles that you've noticed already? Any ideas? Exploration. These are meant for exploration. Okay. Intuitive. Expand a little bit further with that. What do you mean by intuitive?
So it seems like the tools that are available, they just have kind of a clear way of using them, and then you can kind of, there's different layers. So I know yesterday when we were talking about our exploration, some of those tools were hidden, and we kind of like expanded on that. But I guess the primary use for the simulations is pretty straightforward.
Okay, pretty straightforward. You can just jump right into it, right? Not a whole lot of teaching before you start using a simulation. Anything else you notice?
Open.
They're open.
Like it can go to many different levels and many places they can go.
Okay, so this open environment, which can be a good thing or it can be a frustrating thing, because, well, it's quite open. So you have to bring some intentionality to it. Not that you have to kind of lay it out for the students, but you have to be prepared to know that it's open and there's things I should be looking for. Anything else?
Is scaffolding built into something?
Scaffolding is actually built into some of this too, which actually helps with the intuitive nature of it. Okay, so, oh my gosh, this is almost 20 years ago. But when this book was published, How People Learn, there was kind of a side mention of basically interesting findings. This was a summary of research in the learning sciences at that time. Actually, in a new iteration of this book, they've added in a lot more sociocultural learning theories as well. But this really kind of put a lot of effort into summarizing cognitive theories and findings. But there's an interesting quote here that comes up about midway through the book. And they talk about curricula, in particular development of curricula, and they mention this say here, one is progressive formalization. One of the new approaches to developing curricula begins with the informal ideas that students bring to school, gradually helps them see ideas can be transformed and formalized. Instructional use encourage students to build on their informal ideas. You can kind of see why I'm actually putting this quote up here, maybe after some of your experiences yesterday. But this is done, this building is done in a gradual manner, but structured, so they can acquire concepts and procedures of a discipline. So let me highlight a couple things here. So this notion of progressive formalization seems like just more academic jargon, but what this really means is, you can kind of see how this approach could be used in things that you're already doing in classroom. Maybe you were already engaged in this work. But in terms of leading off with students using their own words, their own pictures, their own diagrams, or whatever they create, perhaps in this open environment. And then they gradually begin to use these symbols, some that they bring to the table, but others that are maybe suggested or hinted at. And then they learn to use standard conventional algebraic notation. Okay, so this was in How People Learn about 20 years ago. This approach is embedded in a variety of curricular resources. I would argue it also happens to be embedded in the design of a number of PhET simulations. So let's see how this can be used and how you can act upon it in terms of lesson planning. So there is an expectation that students will use their own words, that students will actually investigate something that they can share. And maybe with the representations that are already included with the PhET simulation, they can actually identify relationships and propose those to class. So it gives you ideas of what students see and are attending to. But you're eventually getting here to some of your other more formal mathematical goals. That is one of the approaches here. So this kind of informal to formal approach has also been captured in what's called an iceberg model. Some of you have seen this before. For some of you, this is new. But you can kind of see down, does this actually? Well, down below, the informal, these are actually problem contexts that could be used. You can kind of see at the top, the tip of the iceberg, kind of the formal approach if you're going to solve equations. There are, below the waterline, a number of representations and problem contexts that could be used to help students understand what that actually means if the formal goal was to solve equations. So some of these you can kind of see are familiar, kind of the balance here. Others are a variety of strategies and contexts. Some of these are kind of the arrow string and unwinding equations. You can actually use these paired together also to investigate systems of equations. But what I'm going to have you do in just a moment is kind of, before we get to the math sim that we're actually going to use, is actually consider kind of what are problem contexts that could be used for solving equations. So much like what you had in that quote that was offered from How People Learn, context, concrete, students' language is kind of in this informal realm. There's more mathematical structure. There's models and representations that are more generalizable, the pre-formal. And at the formal, kind of just below the waterline, you can see a variety of strategies where symbols are used. The whole point to this is so that students understand what's at the tip of the iceberg. So if you go to the tip of the iceberg, you can teach the procedures to how to solve equations, but they might not understand why these things work the way they do. They don't have any other connections to make. So they're relying strictly on a particular strategy without maybe thinking about how it relates to something else that they know. So it's really about building connections, which is one of the ways we help build understanding. So consider opportunities. So in this informal, in terms of informal representations, consider opportunities you create in your class for students to bring up their own ideas, to bring up their encounters with a mathematical principle. Sometimes the instruction materials you use have those opportunities built into them. Whether you choose to leverage those or not, it's often up to you. I know often feel the pressure of time and needing to move on. We don't have time to have these discussions, but at least giving students a place to think about relationships that they're already familiar with, to be able to relate those to something else that's coming around the corner is helpful. So it doesn't always have to be a real world context. It can be realistic. It can be something concrete. Math can serve as a context itself. So prior experiences with mathematics, engaging students and recalling some prior knowledge in mathematics can help with this. And even allowing them to, there's a place for the formal language, for the academic language, but also inviting them just to, how would you talk about it in your own words? In science, actually, this occurs when we ask students for explanations of natural phenomena. We don't expect them to have the formal theories in mind yet, maybe, but at least they have ideas of the way the world works and what they observe. So the pre-formal representations, they support connections and communication. This is actually, the more you can engage in this kind of work, in bringing up representations that students can make sense of, the easier it is for them to make sense of the formal mathematics. These tend to be the representations they can talk about more easily. They can explain. It helps actually illustrate the way things work. So these models, these representations, these pre-formal strategies are often generalizable. It's not just specific to a particular context. it actually cuts across many tasks. So these are really the sense-making opportunities within this continuum of progressive formalization. And the mathematical abstractions that are part of our goals for students, especially at the high school and middle school level, these are more abbreviated. They more fall under mathematical conventions. They, when you think of orders of operations, there is no real sense-making way. There's a mathematical convention of the way we represent expressions and the way students operate those. So some of these things you just have to know. But in other cases, there's ways to connect these ideas with the pre-formal representations. So mathematics as a discipline is very compact, very abstract, very often seems abbreviated. It's dense. It creates situations where if students don't understand what all of the symbolization forms or even the structure of let's say how a proof is organized, it's very difficult to make sense of and get entry to. So it's another reason to kind of connect this to some pre-formal strategies and representation. By starting here, if this is kind of your go-to point of, well, we don't have time for anything else, let's just start here and go through this. If it's the first time they're seeing the representation, oftentimes you're expecting them to rely on recall. That there's very little opportunities to understand what they're doing, you just got to know it, right? Starting at the tip of the iceberg, limited connections to make, got to know it, move on. So hopefully there are some opportunities to connect it to some concepts if you just don't have any other opportunities or no knowledge of what it can be connected to. But let's jump here. So this is our kind of tip of the iceberg type of goal. And this is going to motivate our look at a particular simulation today. And one question is, this is just like a two-step equation, right? So in terms of solving an equation like this, and all of its various permutations with different coefficients and constants, two things to think about is what's the structure and meaning in these symbols? Like what are some things you should see rather than it's just an equation? And then what are some meaningful strategies that could be used? So what are some strategies that you use with two-step equations when you're working with students? So given the range of grade levels you teach, you all encounter this at some point. What are some things that you use with students when you teach this particular topic?